Hello, thank you for having me at Smart City 360. I'd like to talk to you about the Array of Things project and other work that we've been doing in the Chicago area. In particular, 6 lessons that we have picked up over the last 10 years or so, working with Chicago, but also talking with city planners and architects, city managers and researchers around the globe at over 100 different over 100 different cities. So the Array of Things project is a project that began in 2014, funded by the National Science Foundation of the United States. We are currently in a follow-on project called SAGE that I'll also talk about. But the project Array of Things was a experimental instrument where we were interested in learning how we might build a citywide measurement instrument that would serve residents and scientists and those who operate cities, the city managers, equally, that would serve those 3 different constituencies, if you will. So we have one of the things that we have done with the Array of Things project and all of the other projects is we've thought a lot about what it means for a city to be smart. That is the way that people tend to describe these projects. I want to challenge you that there's consequences to what sort of analogy that we use, what sort of architecture or model that we use for cities. And just straight out say, while there are some similarities between a city and a computer, cities are not computers. There are similarities between a city and an organism. Cities are not organisms either. As it's said, all models are wrong, some are useful. There's another way to think about these smart cities, if you will, and it comes from the Rockefeller 100 Resilient Cities program, which took place about 6 or 7 years ago. And what I like about it is, so I do like on the left, you see the city of Barcelona and the City Protocol Society that came out of the leaders there, organizing people, myself included, from around the world. I do like this hierarchical view of a city that shows all of the really important layers, if you will, the environment, infrastructure, built domain, the economy and culture, information and people and various, individuals, families, companies, organizations. So I do like the way that captures a view of the city. I like about the Arab framework, however, is that it goes beyond the structure of the city itself and talks more about what you can see in the city itself and infrastructure and environment, and talks as much, or if not more, about what the city is there for, why cities exist. In the lower right quadrant of the city resilience framework, you can see economy and society. Can you say that a city is smart if it's difficult for people to find jobs or start companies in that city? Probably not. Would you say a city is smart if its residents didn't have access to adequate health care, or if the conditions of living in that city were unhealthy? Probably not. Would you say that a city is smart if its leaders didn't think 10, 20, 50 years down the road as they make their decisions? I'd say probably not. And so I like this approach where it's an aspirational approach that says, smart city is fine, but how do we move the city in the direction that it needs to go in order to fulfill these aspirations of why cities exist to begin with, for people to have lives and to contribute to the economy and to one another. One of the fundamental problems with the city as a computer analogy that I'll say challenge that we have to always be aware of is that a computer only runs if there's an operating system. And a good operating system is a controlling totalitarian system. And so if you take the city as a computer too far, you end up with situations where something that might have started out as a good idea from a public safety point of view actually turns out to be a surveillance technology that has as far downsides as the upsides of safety. So as we've thought about how to deploy infrastructure in Chicago, we've really thought carefully about not just our own intention for that technology, but also what could be done with the technology if we were not involved. We're going to put these things up on poles. Our goal was to put several hundred devices up on poles. Years down the road, when we're off on another project, and maybe that's operated by the city or something similar, operated by the city or by a company, what are the downsides of that, and how do we take advantage of this new technology, machine learning, computer vision, how do we take advantage of that for good things while building in and embedding policy and architecture to minimize the possibility of abuse of those things. And a lot of that, as I'll talk about throughout this next few minutes, is engaging with the community. Now, here you see I've tilted Chicago to the left 90 degrees, so north is to the left, and these are the 130 or so array of things devices. They're all identical, or well, they're two different generations of device, but more or less identical in their sensors and their capabilities. The only reason for the different shapes and colors is that the purpose for putting a device at that particular location came from a science group, a community group, a city department, and they wanted a device at that location for a specific purpose. If you look at the green boxes along the top, that's the shore of Lake Michigan. Those green boxes, along with the ones that are going from top to bottom in the middle, are those were locations that were selected by atmospheric scientists, weather experts, and they were interested in the effect of large bodies of water on adjacent cities. And so with respect to temperature and weather, as well as air quality and in the flow of air through the city. So another example you can see in the Chicago Loop at the top in the blue box, that's the Chicago Downtown Business District kind of blown out. And those devices there are targeting pedestrian safety. So they're looking at, they're overseeing intersections in a busy downtown area. So community driven comes in here because we didn't just talk to the city of Chicago and to a bunch of our science friends, but we also talked to community groups and asked them, what are your priorities for your neighborhood? Might be a concern about traffic safety. It might be a concern about noise. It might be air pollution. And so that conversation was happening throughout, and about about a dozen of these nodes, almost 10%, are located because a community group or an individual in the community said, we would really like to have one at this location because we're concerned about this or that. We also learned in talking with other groups, other academic groups that had worked in the city of Chicago, we asked them, what's the most effective way that we can engage the community? What are the strategies for getting together? For what do you do at a community meeting that's the most effective? And what we heard from multiple groups is that they, for the most part, and we found this as well, residents of the city of Chicago were enthusiastic about supporting science that would aim at helping to make the city better for them. But they're also very interested in having their kids get interested in science. And so they said, please do work with our youth, put programs together that will engage our youth and get them interested in science and engineering. You can see a picture there in the lower right of several students and a faculty member at Lane Technical High School, which is on the north side of the city of Chicago, a school with about 4,500 students. And we've trained over 1,000 students there in how to think about measurement and science, whether that's atmospheric or environmental science or computer science. We've engaged these students to design and build their own wireless sensor device and then deploy that. In some cases, we deployed at the school, in other cases at locations like the Wrigley Field baseball stadium. And this gave students a chance to do an experiment that involved computing and electronics, but also to become empowered to say, I now know how to build a measurement device that I can use to get data about something that I want to learn about my neighborhood or about my city. So this second lesson, community driven, is really key to the success of a project like this, where you're deploying technology throughout a city. Equally important is not just to be community driven, but I would say to avoid being technology solution driven. By that, I mean to approach the city and define, or to residents, and to find in conversations with them, what are the things that they're interested in. Our project, this was perhaps a little bit easier for us because our project started out with the aspiration that we would want to experiment with a citywide instrument using relatively low-cost technologies to add data that would be helpful to residents or community groups, companies, or the city. And so we went to science communities, we went to community organizations in the city of Chicago, we went to Chicago departments and agencies, and we asked, what are your challenges? And we said, we are wanting to design a citywide instrument with a bunch of devices that will all do the same thing. And so for your concern about your neighborhood, for your science experiment, or for your policy needs, depending on who we were talking to, we asked, what should these devices do? What should they measure? What functions should they deploy? And we found that there were two different types of measurements that characterized those discussions. The first, as you would see in any sensor network project, is there were many things that we could go out and buy sensors to measure, from air quality to noise to atmospheric sciences and weather. But there were other things that were of interest, and these were things that are typically measured by a human with their judgment and their eyes and ears, examining what's happening in a park or at an intersection or some other venue in the city. And we called those software-defined sensors, with the notion that we have these cameras that are going out. There's one pointed up and one pointed down at the streetscape, typically from about 9 to 10 meters above the sidewalk. And as that camera takes an image of the scene, we wanted to have the computer do the observing. So have the computer observe what percentage of people might use a crosswalk at an intersection, or what amount of flooding there might be near a park. So this notion of a software-defined sensor meant that we had to build in computing within the device, what we call typically edge computing, in order to do that processing out there at the edge. And there were a couple reasons for doing the processing in situ or at the edge, one of which was at the time we put this in, and still I think it's the case today, to stream video from hundreds of devices over a public network would be extremely expensive. Similarly, saving that video or a set of images over time opens up the possibility that later, down the road, in years in the future, months in the future, that data could be used to retrospectively surveil the city. We didn't want to build up a surveillance database. A third advantage to doing the computing at the edge is that we wanted to support real-time experiments. Imagine a transportation group that wants to develop a responsive street light that will change its timing or delay changing from red to green, for example, based on the safety conditions that are being observed right there in real time. And for those kind of real-time applications, maybe talking to and from vehicles, the round trip to go back to a data center, do some computing, and then come back to the device was too much time to do the kind of real-time experiments that we anticipated people would want to do. The last thing that we gain, or I'll say the fourth thing that we gain from doing the computing locally there, is it gives us a very strong architecture to enforce strong policy with respect to privacy. And the policy, which we developed, again, in partnership with the community and with the city of Chicago, the privacy policy allows us to analyze images or sound inside the device. And after that analysis is done, we have to delete that image or that sound. So it's an image or set of images that gets analyzed and deleted, and there's no record that's being kept in some data vault somewhere. It also, the policy also is particularly strong in that we decided that rather than take the approach that many policies do, which says we won't do this, that, or this thing. We won't do these 12 things. Well, that means we can do infinity minus 12 or an infinite number of things within that policy. We wanted to reverse that and say, no, these are the only things that we will do with these images or sound, and we won't do anything other than the things that are on this list. And when we add something to that list, we'll go through a review process with external advisors, and that review process will be public, and we will then add to that list. So pre-approved applications, a finite list, openly published was really key to that policy that we instilled or instituted in 2016 after a 6-month public comment period where we took some 400 questions and suggestions and turned those into a public document so that anyone could see the process we went through and could see the consideration we took to these various concerns or suggestions. And the accountability was really key. This is our external advisory team that is representative of community organizations, scientists, as well as companies and several current and former employees of the city of Chicago, leaders from the city of Chicago. So let me give you an example of software-defined sensor and what I mean by the type of publication that we do, that this is what we do or don't do. So here what we see is this is a project that's actually happened out at Northern Illinois University, just outside of Chicago. And the approved application allows them to count pedestrians, to count the number of those pedestrians that cross the street and the number of those that use the crosswalk. And they can also save the walking paths of those pedestrians. There are some things that they can't do, anything that's not written here. For example, no license plate recognition, no facial recognition, nothing other than what's written here. And yet there's a lot of useful science and policy that can come despite these very strongly constrained operations that can be done with the images. You can see right here, well, fair number of people not using the crosswalk. And so that might tell a transportation official that they should put a sign, put a light here, or maybe use a scramble crosswalk or some other intervention based on data. And because this is done in a device, what you see here is the result of a couple of hours of experiment, which is not much better than if somebody were standing there. But to have this operating ongoing over months and months allows you to develop over time a sense for what's normal at this intersection and what's abnormal. And that there also allows you to perhaps another software-defined sensor might be, I want to know when the number of pedestrians passing this location exceeds a certain threshold, because that tells me that something interesting is happening. So the fact that these are running all the time and that they cost only a few $1,000s in contrast to how much it would cost to send a human out, and the limited amount of data you get from the human, as are really some of the salient benefits of these types of devices. I mentioned that the Array of Things follow-on project, in fact, is 3 times larger in terms of funding, also funded by the National Science Foundation, goes beyond cities. So you can see some examples of some of the urban measurements that we have. And from left to right at the top is object recognition using computer vision to recognize different types of vehicles. We can, of course, do this in most cases for the type of vehicle, a car, a bus, a bicycle. The current research that we're doing is trying to differentiate between not just an electric vehicle and a traditional oil gas vehicle, but also can we determine from other characteristics whether the vehicle is a rideshare or a private vehicle. And the next one over is street flooding. You can see with your human eyes, based on the texture of the road surface, that there's some flooding on the left. It's difficult to teach a computer to have that same skill that you and I have. The next one over is an example from the skyward facing camera, which is a examination, an experiment that we did to determine whether we could differentiate using that upward facing camera between an aircraft, a bird, and a drone, something for public safety. That was something that we did in partnership with operators of a major sporting stadium in Chicago. On the right, you can see another example of just looking at traffic flow. And then the bottom, I'll mention in an example of non-urban applications. This is a aerial photo, not from one of our devices, of a wildfire. In Southern California, we're working with the University of California, San Diego, who have 100 or so towers around Southern California with cameras and smoke detectors and other sensors. And they're deploying our devices at their towers so that they can get not just real-time information about determining if that's a cloud or if that's smoke from a wildfire that's starting, but also to feed that data into a supercomputer in order to do a faster than real-time model, a digital twin, if you will, of a wildfire based on wind direction and humidity and the state of the fire at any particular point in time. And so this SAGE project takes the Array of Things, edge computing, and software-defined sensing and pushes it out into environmental and other types of contexts. So a couple more lessons from our projects in Chicago, and you can see a theme here that the community has to be really deeply involved. We really are moving in 2 directions with the Array of Things. One I've just talked about, which is the SAGE project, and you can see the Array of Things node at the bottom left there, and on the right-hand side, the SAGE node, much more sophisticated cameras. Obviously, sensors have gotten better in the last 5 years, and so better sensors, also much more powerful computing inside the device. And so that direction, we've just this week started to put up some of these new nodes around the Chicago Array of Things project. You can see the map at the left with the blue circles where all the Array of Things nodes are. We will probably only replace less than half of the 130 or so that you see on the screen there, because we will put these devices in places where there is a science or policy or community concern that's really specific to a place, as opposed to a general urban question like air quality in general or urban heat. Now, in parallel to that, we've been working with Microsoft Research and JC2Co. JC2Co operates 2,600 bus shelters in Chicago. Microsoft Research has created a prototype device, about $100, that measures air quality. And we worked with these partners as well as the Environmental Law and Policy Center and, of course, the city of Chicago to design a deployment of 115 of these devices, these $100 air quality devices. They also do temperature and light. And we designed a scheme that you see there in the middle, where we put 115 of these up in June of this year. That was important because many of the things that we heard from people in cities around the world that were of concern to them, urban heat island, where you want to do temperature and light intensity, air quality and air pollution and noise, these are things that don't need the powerful edge computing devices that something else does, as I've talked about before. And so we can go with lower cost devices, but put many more of them in. So our long-term aspiration for Chicago is to get probably 50 to 70 of the Sage nodes, but to have 10 times as many of the lower cost devices like we've been prototyping in partnership with Microsoft Research. The other part of this really is lesson number 6. You can see this on the right-hand side, this green sticker that's going up on the bus shelters, on the black version of it in the lower left here. This 6th lesson is in the Array of Things project, we were mostly targeting the city of Chicago as a data consumer and then relying on their open data portal to get the data out to people. And we were providing an application programming interface as well as bulk download to anyone that was interested, but really tuned to the science community. Turns out that open data portals are great, but they're not the best way to get information out to a person on the street, just a resident of the city. And so making data legible is also part of what we feel like is necessary as the next step to these kind of measurement devices. And it was one of the things that appealed to us about working with the Microsoft, it's called Eclipse, the Microsoft Research Project, is that they also thought about this. And so at these bus shelters, that QR code, anyone with a device can scan the QR code and then get a map of the city, get information about air quality at that particular bus shelter over the past day or two, and then get educational information about air quality as well. What does it mean if PM 2.5 is measured at 36, what is a microgram per meter cubed? What does that mean for my health? So a way to get information out into the hands of the people who live in the city. So that was a real key to this particular partnership. So again, 6 lessons, maybe not the only 6, but certainly the ones that have bubbled to the surface repeatedly over the last almost 10 years that we've been working in Chicago to do these kind of projects. So thank you again for having me here. And I hope that you'll enjoy the rest of the afternoon. Thanks again.